Pleasure to introduce again Professor Howe. But know that I was his student, and actually I am his student since 19. So let's enjoy his lecture.
Okay, so as I was starting to say, yesterday I told you about some things about theta correspondences, and I told you the history of, in the theory of automorphic forms that led up to, that preceded the idea of dual pairs and theta correspondences, and then I stated for you what dual pairs were, what the idea was, and what the main facts were, and noted that the main constructions in the theory of automorphic forms up to that time had all been cases of that kind of correspondence. But I didn't tell you anything about where the ideas came from. So that's what I want to focus on today. So, I did emphasize that representation theory got its a big boost from physics, and then people realized that representation theory was also responsible, was also sort of sitting behind the theory of automorphic forms. So that's where we were. And now I'd like to talk about where the ideas of a dual pair came from. And this really didn't start in automorphic forms. It really started with physics, and in particular with quantum mechanics, and also with classical invariant theory. And both of these things are places where Hermann Weyl had a substantial influence, and he made several steps sort of towards the direction of the idea of dual pairs, but he didn't quite make the final step. So people around the turn of the century, people began to understand that classical mechanics sort of failed at very small scales, and you had to think about really tiny particles in a different way from classical mechanics. And actually the yoga developed that a particle is not really, particle had always been thought of as a point mass, but people realized you couldn't really think of it that way. You had to think of it as sort of spread out over space. It was some kind of probability distribution. Might be here, might be there, according to some relative probabilities. But still, you wanted to be able to talk about position and momentum. People, they needed to measure things for, and to get results out of experiments. So, what they came to was that particles are sort of elements of L2 of Rn. They're sort of functions on Rn, or probability distributions, and the position and the momentum are some sort of things you do to those particles, and then you somehow get a number out of that. And the idea was, so this led in 1926, so quantum mechanics had sort of been under development for over a quarter of a century at that time. But in 1926, Werner Heisenberg sort of codified some essential relationships that were sort of implicit or needed for quantum mechanics. And so So you want to consider a system of 3 particles in space. If it's 3 space, then you need 3p variables, which we'll call n, to specify the particles. And so you want some operators, qi, to tell you how to compute the position, some other operators, pi, to tell you how to compute the momentum. It's plausible. I mean, if you want to think about an operation which would tell you the position, I mean, if you had a point particle, a point mass at some point, and you multiplied by the ith coordinate, then it would multiply that particle exactly by that. And so it's plausible to think that the qi's should be multiplications by the xi's. And then, the pi's then could be differentiation. They tell you how things are moving, how things are changing. Here I'm sort of ignoring the masses, and so pi really is sort of the velocity, not the momentum, but we'll ignore that subtlety. So Heisenberg observed that so these operators don't commute with each other, and this means that you can't talk simultaneously about the position and the momentum. So, if you have a particle, if you want to measure where it is, you sort of have to stop it, right? So you've changed the momentum, and if you want to measure how it's moving, you have to let it move so it doesn't stay in the same place. So these operations are sort of incompatible, and Heisenberg sort of came to the mathematical formulation of that so that these guys don't commute, but their failure to commute is not so incomprehensible. If you look formally at the commutator, if you look at the guys in opposite orders and take the difference, then it's just the identity. If they're the same coordinate, if they're different coordinates, doesn't matter. If you can measure the momentum in one direction and the position with respect to another coordinate, it's not a problem. So Heisenberg sort of identified these relationships as being fundamental for mathematizing quantum mechanics. And they've definitely come to occupy a central place in mathematics and physics, and they're known as the Heisenberg canonical commutation relations, or the CCR. Okay, so in the late 1920s, Hermann Weyl, Weyl was an expert in Lie groups. I mean, what we know him, one of the things we know him for, of course, is the Weyl character formula. So he had studied Lie groups in detail, and especially compact groups. And he was following physics at that time, and he observed that the CCR actually defined a Lie algebra. And there's a group associated to that algebra, and the group would have dimension 2n, the total number of twice the number of variables plus one more for the identity. So that's the one-dimensional center. And then the commutator operation on the complement to the center is skew symmetric, and there's always one guy which doesn't commute with some other guy. So it's a skew symmetric operation which is non-degenerate, and that gives rise to a symplectic vector space. So the physicists at that time were not used to thinking about groups, and they thought the idea of a group, a Lie group associated to this, was very exotic. So they called this, the associated group, the Weyl integrated form of the CCR, but we just call it the Heisenberg group. Okay. So the value, I mean, it might seem just like a formal thing, introducing this group, rather than just the operators themselves, but the value of thinking about the group soon showed itself in a basic uniqueness theorem that so it's part of the basis of quantum mechanics, and it's come to occupy a very important place in representation theory also. So it's the Stone-von Neumann theorem, and it was established independently by Marshall Stone of the University of Chicago and John von Neumann of the Institute for Advanced Study. And actually, von Neumann wasn't in the US yet. I think he was still in Vienna, but because this was around 1930. And so we can observe that if we want to look at the group generated by these operators, the exponentials of the differentiations are just translation operators on Rn, and they act as unitary operators on L2. And also, well, the imaginary exponentials of the coordinate functions are also unitary, and they act by multiplication on L2 of Rn. So you've got these unitary operators acting on Rn, and they sit inside this this group, this 2n plus 1 dimensional nilpotent group. And what Stone and von Neumann showed was first that this action is irreducible, that from any piece of L2 of Rn, if you let the group act, you recover the whole space. So the total picture is kind of unavoidable. If you allow for the action of Hn, you have to consider the whole space L2 of Rn. And besides that, I mean, this is sort of the real kicker, that if you have any irreducible representation of the Heisenberg group, in which the center, the scalar operators, act in the same way, then that is unitarily equivalent to this action. So there's only one of these actions. So it's a very, very strong uniqueness theorem for this particular representation. And that uniqueness has played, a key role in all the developments since. And besides, okay, so Hermann Weyl sort of meddled again, and besides noting that there was this Lie algebra and there was an associated group, he also looked at the associative algebra generated by the PIs and the QIs, and this algebra has come to be pretty important, and so it's now called the Weyl algebra. And concretely, what it is it's the algebra of linear differential operators with polynomial coefficients. And if you start with W, with the Heisenberg Lie algebra, with the P's and the Q's as the first thing, as the generators for this, and you start looking at more and more complicated operators, you see that this algebra has a natural filtration. So what you do is you let W upper A stand for the span of all products of A full or less copies of the PIs and the QIs. And then it's clear that this is an algebra filtration in the sense that if I multiply something in WA with something in WB, I get something in WA plus B. And if you look at the associated graded algebra, it's just the symmetric algebra, or what's essentially the same thing, since the symplectic space is self-dual. It's the polynomial algebra on the symplectic vector space. Okay, but we want to look at the non-abelian aspects of this a little bit more. And so the Heisenberg commutation relations imply that if you take commutators of things in W1, you get something in W0, just the scalar operators. And then, so if you follow that through and you look, say, well, what happens if I take a commutator of something in WA with something in WB? Well, I mean, you're probably not interested in doing that very much for large A and B, but you can ask what happens. And what happens is that you lose 2 degrees because, so this is W0, it's 1 plus 1 minus 2. And that relationship propagates through, and the commutator of something in WA with something in WB is in WA plus B minus 2. Again, for large A and B, that's not so terribly interesting, but if you look at W2, this says that W2, commutators with W2 is again contained in W2. So W2 is a Lie algebra. So we started with W1 being a Lie algebra, but W2 is considerably bigger, and it's also a Lie algebra. So what Lie algebra is it? Well, you can also observe that if I take the commutator of something in W1 with something in W2 with W1, I'll get inside W1. So W2 is acting naturally on W1. And so W1 self-commutators land you down in W0. So if you look at the action on W1 modulo W0, which is this symplectic vector space, you get this action of W2 modulo W1, and it's pretty automatic that it will give you operators that preserve the symplectic form, and in fact, it's an isomorphism of W2 modulo W1 with the symplectic Lie algebra. So then this can be exponentiated to an action of sp2n, the group, on Hn by automorphisms. And those automorphisms will act trivially in the center, so they will convert the standard representation of Heisenberg into some other representation which has the same central character, so it will be unitarily equivalent. It'll essentially be the same representation. So that means there has to be a unitary operator that takes you from the one action to the other action. So you're going to get this mapping of the symplectic group into the unitary operators that act according to their action on the center, or on the on the Heisenberg group. So what you've got here is essentially you've got the Heisenberg group, and then it's contained in this larger group, which also has a piece isomorphic to the symplectic group. And so this is a group extension, a smaller group inside a bigger group. And the theory of extending representations from a group to a larger group was studied, the general problem of that was studied by G.W. Mackey, and he showed, he analyzed what happened, and in this case, it gives rise to the oscillator representation. So now if we go back to the Weyl algebra, Mackey didn't do this theorem explicitly. Well, Mackey wrote a paper that pointed out that the theorem of Stone and von Neumann could be generalized to a much more general situation where you considered the product or the action of an abelian group and its Pontryagin dual, and then any automorphisms of that you would get a representation of that, and that implicitly contains the Weyl representation, the oscillator representation, but he didn't focus on that specific case. So what Wey's contribution was essentially focusing on that case, and also, as I said yesterday, it had been done earlier by David Shale for the real field, for the Heisenberg group over R, but Weyl treated the Heisenberg group over an arbitrary local field, and that hadn't been done, strictly speaking, before. Okay, so it turns out that we can find inside W2, we can find a complement to W1, which is isomorphic to the symplectic Lie algebra. Actually, general results on Lie algebras tell you you should be able to do that, and specifically how you do it in this case is you take the symmetrized twofold products of the QIs and the PIs. So you take the products PI, PJ, the products QI, QJ, and then the symmetrized products of the QIs and the PJs, which will essentially be linear vector fields, but then you have this little extra constant there. And that constant is related to the, it's not equal to the co-cycle, the fact that you need this twofold extension, but it is related to that. So essentially what the constant does is when you exponentiate these guys, you get the unitary action of GLN on L2 of Rn. But so these guys normalize it so it becomes a unitary action. So you have to multiply. If you expand everything, then you have to divide by the determinant to get rid of the. You've increased the inner product, and you have to divide by the determinant or the square root of the determinant to make it unitary. Okay, so if you want to be, this is just being a little more explicit about things, so that if we set U plus or SP20 equal the span of the QI QJs, and U minus or SP02 to the span of the PI PJs, and then SP11 to the span of the mixed operators, then this gives you sort of a grading of the symplectic Lie algebra into two pieces that are very simple. They're commutative, and then they're normalized by the third piece, which is GLN. And then the commutators of the things in the plus and the minus land inside the GLN. So this is actually a grading of the symplectic Lie algebra. Okay, so if you want to sort of get a concrete picture of what things are, what's happening here, if you exponentiate the multiplication operators, what you'll get is multiplication by imaginary quadratic exponentials, and if you multiply the quadratic differentiations, you'll get the corresponding convolution operators. And then for the 1-1 part, you'll get the standard unitarized action of GLN on L2 of Rn. Okay, so, oops. Yeah, so I mean okay, so anyway, this is a way to sort of concretely realize the oscillator representation on the pieces. What is the subtle thing is how the pieces fit together to make the total representation. Okay, so Weyl did all these things. He introduced the thinking about the Heisenberg, the commutation relations as a Lie algebra. He pointed out there was an associated group, and then he developed this algebra of polynomial coefficient differential operators. And this was all in the late 20s. But in the 1930s, he seems to have forgotten about physics, and he focused on invariant theory. And this is sort of, he wrote up his conclusions in a book, which is still, I think it's still in print, The Classical Groups. Here in this book, he formulates the idea of the first fundamental theorem of invariant theory, which is that you take some group acting on some vector space, and then you take as many copies, you take arbitrarily many copies of this vector space, and you want to describe what are some generators for the invariant polynomials on arbitrarily many copies of the vector space. And if the representation is not self-dual, you should also throw in the dual representation. That's a very sort of demanding task. I mean, as the number of copies goes up in a typical action, the variables there'll be more and more generators, and they'll get more and more complicated. But what Weyl found was if you just take the defining modules, so Cn for GLN, or the orthogonal space for On, or the symplectic space for SP2N, if you just take those modules and you take many, many copies, then he could say something. And what his result was that if you take a standard action, I mean action on a certain number of copies of the defining vector space. So if you take a standard action and you take many, many copies, then a set of generators for the invariant functions of G on this sum is just given by the pairings, right? So if you've got an orthogonal group, you take vectors from two different copies of your module, and you look at the inner product. And so this will give you a certain number of quadratic functions, and they will generate all the invariant functions. And it's the same for the symplectic group. And in the case of GLN, you take one of the vectors in V and the other vector in V star. You can't pair V with itself. You have to do it with a dual. So that's why you need the dual in the case of GLN. Okay. So how does this all connect with dual pairs? And one of the key observations is that, so if you have a dual pair in the symplectic group, then the action of G on the associated graded algebra of the Weyl algebra is a classical action. Okay, so dual pairs and classical actions are sort of almost interchangeable. And the converse is also true. If you have a classical action on a space G, and you look at the image of G in the symplectic group of the space together with its dual, then G will belong to a dual pair inside that large symplectic group. So there's this intimate relationship with of standard actions and dual pairs. But again, this is sort of a posteriori. It doesn't tell you why you might want to do this. So if you then have a dual pair inside the symplectic group, and you look at, you can ask, so what are going to be the operators that commute with, the invariants for the action on the Weyl algebra are the operators that commute with G. And so what are they going to be? Well, what Weyl's theorem says is that they will be generated by the order 2 guys. But the order 2 guys is the symplectic Lie algebra. And so you want to look at the guys in the symplectic Lie algebra that are invariant by this group G, and what is that? That's exactly the subalgebra of the symplectic Lie algebra, consisting of things that commute with G. And from that, it's not too far to see that if you reverse the situation, the theorem then is that the G prime, the centralizer of G in the symplectic Lie algebra, is going to generate the full commuting algebra inside the Weyl algebra of G. And so you've got G and you've got this G prime, and from there they have this very beautiful relationship, and then it's not too big a jump to then look at the Lie algebra of G prime and say, well, the Lie algebra of G prime is certainly going to commute with, the Lie algebra of G is certainly going to commute with G prime, and in fact it's the full centralizer in there. So that the Lie algebra of G and the Lie algebra of G prime actually form then a dual pair inside the symplectic Lie algebra. This was sort of the origin for me of the idea of a dual pair. So there you are. So you've got G, and then you've got this commuting algebra, and so a corollary of this is that since G is acting by linear operators, the G prime is going to have this grading. It's going to have the 2-0 component and the 0-2 component and the 1-1 component, and it's going to generate the full commuting algebra of G. So that means that the joint action of G and this G prime is going to be irreducible on any isotypic component for G. So you take an irreducible representation for G, and you look at all the pieces of the Weyl algebra that are isomorphic to that, and then or on the basic module, and then and then G prime is going to act irreducibly on that. So you can use that to analyze what the structure is going to be, and so if you have something in this particular isotypic component, and you're acting by G prime, you can act by the differential operators and lower its degree, and lower its degree, and lower its degree, until you can't lower its degree anymore. You're going to get 0. So at some point that will stop. So you want to look at the operators that would be killed by G prime 0, 2. The lowering operators or the differential operators in G prime. And then, because G prime acts irreducibly, if you take this space here, and then you start acting by the full G prime, then you get the raising operators, and they will generate the whole thing. What's slightly less obvious, but not very hard to establish, is that if you look at the joint action of G and G prime 1, 1 on these lowest guys, I've written them as H for harmonics. If you look at the joint action of G and G prime 1, 1 on that, then that's irreducible. So, this is some very, very extensive generalization of the classical theory of spherical harmonics. And I'll just remind you what that was or is. So in this case, you take the orthogonal group acting on one copy of its vector space. So you look at the polynomials there, and then you have the R squared, the invariant metric that will commute with G, and you have the Laplace operator, which will also commute with G. And so this was an observation, an important observation of the people in the late 18th century, early 19th century, that the Laplace operator was invariant under rotations, and so you would get these spaces of harmonic polynomials of various degrees that were representations for the orthogonal group, in this case O3. And then the other operator in SL2 is just the commutator of those two guys, which is basically the Euler degree operator, then again modified by this constant. So what you conclude here is, so the standard theory of spherical harmonics says that every polynomial is uniquely a sum of powers of R squared times harmonic polynomials. So you start with the harmonics and you multiply by R squared as many times as you want, and then if you act by the Laplace operator, you'll just come down that chain. So that's because they form this Lie algebra. So you're getting these irreducible representations of lowest lowest weight type for SL2. This is one very special case for the ON SL2, and there's an analogous theorem for any classical group and its dual. This is just an aside, but it also turns out that Huygens principle, which is another important observation from very classical mechanics, comes from the 17th century. And what it says is that to understand wave propagation, that says waves from a point source spread along spheres, so that you get a blink, and then the light from that blink spreads out and it lives on this very, very thin sphere, and when that sphere reaches your eye, you see it, and then it moves on and you don't see it anymore. Basically, Huygens principle says that when you flip the switch off, the lights go off. This is actually not true in 2 dimensions. If you think about throwing a pebble in the water, you don't get just one ripple going out, you get a whole series of ripples sort of going out. So once the first one reaches you, you continue wobbling for quite a while, less and less, but still. But in 3 dimensions, it doesn't happen. The lights go out. And it turns out that Huygens principle is true in odd space or even space-time dimensions. Oh, sorry, this I've got this reversed. Odd space, even space-time dimensions, but false in even space dimensions, which is odd space-time. And it turns out that this is a somewhat subtle aspect of the theta correspondence for the dual pair ON1SL2. So that's just a side remark, but I like it, so put it in. So another way of looking at this business is that it is a theory of holomorphic representations. So as I mentioned yesterday, sort of holomorphic representations were the basis for the holomorphicity of the modular forms that people were studying in the 19th century. And then they were, when Harish-Chandra wanted to create discrete series for a general group, the first thing he did was create analogs of holomorphic representations, and then he realized that more were needed. But the holomorphic representations have played sort of, they're one of the easiest classes of representations to get your hands on, and they played kind of a special or notable role in representation theory. And in the early 1970s, several papers were written sort of independently by Stephen Gelbart and Ray Kunze and Ken Gross and Masaki Kashiwara and Michel Vergne, which showed how to realize these holomorphic representations on spaces of polynomials. And all of them, in fact, can be realized as the G-isotypic components of representations coming from dual pairs. And so here I'm just reminding you, holomorphic discrete series were the first discrete series representations constructed by Harish-Chandra, but he soon realized there must be other ones. And holomorphic representations don't have to be discrete series. Some of them can be very, very small. I'll talk more about size of representations a little bit in a few minutes. These constructions of Gelbart and Gross Kunze and Kashiwara Verne all come from dual pairs. And sort of when I realized this, I thought, it seemed to me, there seems to be something going on here. So I thought about the situation, tried to think about it more generally. And this is not at all a direct consequence of those things, but later on, I teamed up, I sort of helped Tom Enright and Nolan Wallach show that, in fact, all holomorphic representations of a classical group arise from dual pairs. So that's a sort of a classification of holomorphic representations. So I'd like to talk about one notion of size of representations, and this is a notion of size that I guess I'm the one that mainly talks about it. I call it rank. And if you have an irreducible dual pair in the symplectic group, if one of them is very small and the other one is very big, we have these. We have these pairs like sp2n and OM, and the n and the m can vary independently. So you can have one of them be very big and the other one be rather small. And if one of them is very much smaller than the other, then the representations of the big group that come from the dual pair will be quite small as representations of the big group, and they can be characterized by natural spectral properties. So what are these properties? So if you look, so you look at sp2nr and opq with p plus q less than n. Then in sp2n, there's a maximal parabolic that was singled out by Siegel. It's called the Siegel parabolic, and its unipotent radical is it's related to the Siegel upper half space, and the unipotent radical of this Siegel parabolic is the real symmetric n by n matrices, and it will act on the Siegel upper half space just by translating the real part. And the representations of sp2n, if you take them, if you restrict them to U, so U is this commutative, it's this abelian group, which is isomorphic to the symmetric matrices, and it's got this GLN, that's the other piece of the parabolic, acting on it. So the spectrum of the restriction is going to be invariant under the GLN, so it's going to be the same on each isomorphism class of symmetric matrices. So you can specify the spectral nature of the representation by saying, attaching an integer, a multiplicity, to each one of the orbits. Okay. So there's a few orbits in there, the maximal rank guys that are sort of open, and then everything else sort of fills out the cracks in between. And we can say that the representation has small rank if the multiplicity of the big orbits is 0. In this case, turns out that there'll be a unique orbit of maximal rank that appears, and it will have some signature. And then there's a theorem that's, so I proved a special case by a very complicated argument, and Zhen-Su Li found a very beautiful, clean, general argument that shows that this is stated for the symplectic group, but there's something similar for other classical groups, that so the part of the unitary dual which is supported on this the closure of this small orbit is in bijection. So the dual pair, the theta correspondence in this case, sort of injects the unitary dual of the orthogonal group into the piece of the unitary dual of the symplectic group that behaves this way under restriction to the Siegel unipotent radical. So I like this. I like this picture very much. I should remark that together with Shamgar Garevich, we've shown that a very similar picture works in the finite field case. The finite field case, there is not completely canonically defined theta correspondence, but you can use this technique in the case of very different sizes to construct a class of representations of the big group in a similar way. Okay. So I like this picture because it gives you this sort of way of thinking about the unitary dual. So you have the unitary dual, and then you have all these little pieces inside that are themselves the unitary duals of smaller groups. And then they will have pieces inside them that are unitary duals of still smaller groups. And so this kind of provides a kind of a fractal picture of at least part of the unitary dual. And I find that I like that. But unfortunately, the notion of rank does not fit very well with the techniques that are used in the ATLAS project, which is currently the main effort to classify the unitary dual of reductive Lie groups. And so it's sort of just sort of sitting there on the side. And we'll see what happens eventually. However, a team, I hope I've got everybody here, Dan Barbash and Jajun Ma and Bin Yong Sung and Chenbo Zhu have succeeded in using the theta correspondences to establish the unitarity of a key class of representations of the type that are called special unipotent. And the ATLAS project is very focused on these representations, and this is a big boost for the ATLAS project. And okay, so that's more or less it, but I just want to say one more thing about dual pairs. And it turns out, so when I came to write this up, the idea of a supergroup was very much a la mode. And so what is a supergroup? It's a Lie algebra. It's a graded Lie algebra. So you have a Lie algebra piece, and then you have another piece where you take anti-commutators, and the anti-commutators land you back in the Lie algebra. And that's called a Lie superalgebra. And so there is an analog of the Lie superalgebra based on the sum of the symplectic Lie algebra and the orthogonal one. So the orthogonal Lie algebras act naturally on exterior algebras, just like symplectic Lie algebra can act naturally on polynomial rings. And so it turns out that there's a version of dual pairs, and unfortunately this version is not totally symmetric. So this is a duality between a standard action of a classical group and then the action of some superalgebra which generates its commutator inside this large superalgebra. But it includes a skew duality for dual pairs, and it implies some basic results in cohomology theory, like the de Rham decomposition and the Hodge decomposition. So this is not very much has been done with this, but it does have some connection with very standard mathematics. And I think that's it. Oh, not quite. Oh, yeah. So I should say something about proofs. The first thing is about Weyl, and his proof of the FFT was pretty convoluted, and it used these identities known as the Capelli identities, which are kind of mysterious. A paper of Attia, Bott, and Patodi talking about the index theorem referred to them as the mysterious Capelli identities. It turns out that there's a cleaner way to approach these things. And if you if you want to think about GLN-GLM duality, you can establish that directly using the theory of multiplicity-free actions, and then you can use that result, GLN-GLM duality, to establish the other FFTs. But the Capelli identities sort of have interest in themselves, so the Capelli identities and their parallels for the other classical groups have been explored in quite a bit of detail by Toru Umeda from Kyoto. And also, the dual pair interpretation of the CITs actually implies the Capelli identities, and it reinterprets them as the centers of a homomorphism between the centers of the universal enveloping algebra of the two elements of the dual pairs. And Tomasz Przybinda has a paper making this explicit. Okay. So then a little bit more about the proofs. Well, I didn't say, I stated the duality theorems yesterday, but I didn't say anything about proving them. I won't say much now, but there's two main tools involved. One is that you have to analyze the geometry of the action of the dual pairs on the symplectic vector space with a close attention to the structure of orbits. And I heard somebody talk about the moment map, and the moment. So you have the two. Members of the dual pair acting on the symplectic vector space. There's a moment map to the coadjoint orbits of each one of the groups, and this gives essentially a bijection between the orbits, not quite a bijection, but close to it. And so that's an important component that's an important tool in the proof. The other main thing that's used is some kind of filtration of the representations. So you have to have some way, you sort of establish the theorem is true for some simple-minded representations to begin with, and then you throw those away, and then you look at another stage of representations, and so on and so on. So you go up through these stages of increasingly complex representations. And there's parallel notion in the real case and in the Pierre cases, and this has been quite an important technique for the proofs. And I think that I will leave it there.